This is a discussion on electric field due to a line charge. What does line charge mean? Very simply, charge distributed on a line. So let's consider this arrangement here. We have a rod. On this rod, there is a charge Q, length of the rod is L, and there is a point P here. Somebody asked me to find out field at P due to the rod. Now, the rod is obviously a line charge, and in order to find the field due to this line charge here at this point P here, we have to consider some basic things. The first one of them is lambda. Lambda is charge per unit length, coulomb per meter as you might like to call it. Now, since the charge is uniformly distributed over here, what are we going to do? For this rod, the lambda is going to be Q upon L. The field due to a point charge is KQ upon R squared, where Q is the charge and R is the distance. I know this much. So how do we start? So I divide my rod into point charges. For example, let me draw it in red. There is a point charge here. Now, since this is a very small charge, I would like to call it dq, and there is some distance. I would like to call it as x. Now, I have given the length of this rod as L. The length between the end of the rod and point P, let me show this to you. The length between the end of the rod and point P is going to be A. Let's call this distance as A. Now, what is the distance between the red point charge and the point P? The distance between the red charge and the point P is x. What is the value of charge? That is dq. And what will be the field? The field is simply going to be k dq upon x squared. Now, how much is dq? How do we find dq? So dq is lambda into dx. And why is that? Because lambda is charge per unit length, charge distributed in the length, and dx is the length, this particular length. The length of this part of the rod is dx. So for a length dx, the charge is going to be dq equals to lambda into dx. So I'll replace it, k lambda dx upon x squared. And what will be the direction of field? The direction of field is going to be away if we consider the rod to be positively charged. Now, if we have found out the field due to one charge, that is dq, what about field due to all other charges across the length of the rod? You simply add them, because for any one of them, consider another one here in blue. For this one too, the field is going to be away from the charge at point P. So all fields are in same direction. All we have to do is simply add the magnitudes. In order to add the magnitudes, we do a very simple thing, that we integrate. Now, integration of field, obviously, k lambda dx upon x squared. And what are my integration limits? What is the distance x varying from? So I would say that the smallest possible value, please look at the diagram. The smallest possible value of x from the point P is A, Can you see that? And the largest possible value of the rod, of the other end of the rod from point P, is going to be L plus A. So what are going to be my integration limits? My integration limits are going to be from A to x plus A, and k lambda. What is the integration of dx upon x squared? That is a very simple formula, minus of 1 upon x. Let me change the page here. So the integration was k lambda dx upon x squared from A to x plus A. Sorry, L plus A. Let me draw the diagram again here. This was the rod. The length of rod is L. The point is P. Since the point is P, the distance here between this part of the rod and point P is A. So the closest distance is A, and the farthest distance, as you can see, the closest distance is A and the farthest distance is L plus A. So those are my integration limits, and that is the way I'm going. So electric field is k lambda minus 1 upon x A to L plus A. The integration of dx upon x squared is, all of us know it, is minus 1 upon x. Hence we'll have k lambda. Now since there is a negative sign here, so you can reverse the limits. First the lower minus, then the upper. Okay, we'll have to change it. This is A, not x. Doing this again and again. L plus A. So k lambda L plus A minus A divided by A into L plus A. A and A gets cancelled out. So we'll have k lambda L upon A into L plus A. You might remember what was lambda equals to. Lambda was equals to Q upon L. So lambda into L can be easily written as Q. So the final value of electric field can be written as KQ upon A into L plus A. Let's come now to another situation where I have again a linear charge, that is charge distribution distributed on a length. This is a linear charge, and I draw a perpendicular on the charge, not perpendicular bisector exactly, but just a perpendicular point P. Now this is a linear charge. It has got charge Q, it has got length L, and all the things that you need. Lambda is obviously equals to Q upon L. Lambda is equals to Q, lambda equals to Q upon L, and you want to find out the electric field at point P. Now what are we going to do? Consider a small charge here. Let's say this distance is x. The perpendicular distance is obviously d. This is the perpendicular. I'm saying it again, it's not the perpendicular bisector, it's just the perpendicular. And this charge is dq. Now what will be the field due to this charge dq at point P? The field will be something like this. The red line is showing the direction of field. Let me extend the axis. So if this angle is theta and theta here, and this is your field, the field will have two components. The first component, as you can see, is perpendicular to this charged wire, so we are going to call this component as E perpendicular. And the second component that you are going to see is parallel to this charged wire, so we are going to call that as E parallel. And it's very easy to understand what is E perpendicular equals to. E perpendicular is equals to E cos theta, and E parallel is equals to E sin theta. Now, what is theta equals to and what is E equals to? So we'll look everything step by step. Now, what is E equals to? We know that E is the field due to this charge, and point charge and field due to any point charge is k dq upon r squared, where r is obviously the distance, as you can see. Now, what is the value of r? This right angle triangle here, if you focus on the right angle triangle, you will very easily notice that r is equals to root under x squared upon d squared. So what will be the field again? It will be k dq upon x squared plus d squared. Now, how do we replace dq? That will be equals to k lambda dx upon x squared plus d squared. Now we have to find two fields now. First one of them will be E perpendicular, and E perpendicular will be equals to k lambda dx upon x squared plus d squared cos theta, as you might see here, cos theta. So what would be cos theta equals to? Please focus on the right angle triangle. The cos theta is going to be d upon root under x squared plus d squared. In this page I have simplified this. The perpendicular field is going to be k lambda dx into d upon x squared plus d squared, where this is x, this is d, this is r, and the value of r is obviously root under x squared plus d squared. So this is your E perpendicular. Now how do we solve it? Please take into consideration that for all these charges, all these small charges that are here, each one of them will have a field. Let me draw this in blue, something like this, and each one of them will have a perpendicular component and a parallel component. So in order to find the perpendicular component, we simply integrate one of the perpendicular components, or in simple terms, we add it. So how do we add this thing? Again, focusing on the right angle triangle, here. This is the right angle triangle I am focusing at. So focusing on the right angle triangle, we have x upon d equals to tan theta, and x is equals to d tan theta, and dx will be equals to d sec squared theta d theta. Now back to our solution. So what will be E perpendicular now? K lambda d, all these things don't change, but what about dx? So dx is here, you can write it as d sec squared theta d theta. And if you try to solve the denominator and you substitute the value of x here, that is x equals to d tan theta, you will get d cubed sec cubed theta. So notice that you have 2 d's on the numerator and 3 d's on the denominator, so you'll have perpendicular field as k lambda upon d cos theta d theta, and then you integrate it very simply. And what is the integration of cos theta? That will be k lambda by d into sin theta. Now the question is, what limits are we going to set it up to? I mean, what are the limits of this thing? So coming up to the next, this is my wire, the positively charged linear length, whatever you like to call it. This is the perpendicular here, d. This is the point charge that we were talking about. Again, two fields, perpendicular and parallel, and theta. So I think we got the E perpendicular in the previous page. That was what? K lambda upon D into sine theta. But we needed some kind of integration limits. To look for integration limits, please focus on the diagram. For integration limits, we'll go to the ends of the wire. The lower end of the wire makes an angle, let's say beta, and the upper end of the wire, let's say, makes an angle alpha. Now, since this is the base here, and anytime you consider base reference you consider at 0 degrees, and one of the angle is below 0 degrees and one of the angle is above 0 degrees, and this is very important to understand. Please notice, one of the angles is below 0 degrees, one of the angles is above 0 degrees. So your integration limits are going to be from minus beta to alpha. Minus beta for below 0 degrees, minus beta for below 0 degrees, and alpha for above 0 degrees. So you'll have E perpendicular as K lambda by D. Sine theta is becomes sine alpha minus sine minus beta, and then we solve it. K lambda by D sine alpha plus sine beta. This is the value of E perpendicular. Now what is the value of E parallel? How can we find out E parallel? Same principle, except that E parallel is going to be total field into sine theta. What is E sine theta going to be? Let me first write what E is. Please try to remember, this charge was dq. This distance was root under x squared plus d squared. This distance was root under x squared plus d squared. This distance was x. And what was E? K lambda dx upon r squared. R squared, that was x squared plus d squared. Now we have to multiply this with sine theta. Now what is sine theta? Please take into consideration the right angle triangle. Again, the right angle triangle here. What will be sine theta equals to? Sine theta will be equals to x upon root under x square plus d square. So k lambda x dx upon x squared plus d squared power 3 by 2. Okay, so we were at E parallel, that was equals to k lambda x dx upon x squared plus d squared power 3 by 2. Again, we'll use the same substitution. X upon d equals to tan theta, x equals to d tan theta, dx will be equals to d sec square theta d theta, and we'll substitute it here. So E parallel will become equals to k lambda d tan theta into d sec square theta d theta divided by d cubed sec cube theta. Solving it, you will have k lambda by d sine theta d theta. And now you'll have to integrate it. What is the integration of sine theta? That will be k lambda by d into minus cos theta, and Coming back to our integration limits, I think you might remember the two ends of the wire, forming angles beta and alpha. Let me show this on next page. So I had a wire, again the same diagram. It's getting very annoying drawing this again and again. Anyways, so we were focused on E parallel, E parallel after integration came out to be k lambda by d into minus cos theta. And if you remember the integration limits, they were from beta alpha. Again the same principle, this is your reference, so reference is 0 degrees, below 0 degrees minus beta, above 0 degrees plus alpha. So your E parallel will become equals to k lambda by d cos beta minus cos alpha, and this is your E parallel. So this was the result that we were looking for. The field due to a line charge, it will have two parts perpendicular to the line. This will be the component, perpendicular to the line, and this will be the component parallel to the line. Now this thing has many implications, many implications actually, and we are going to cover some of them, and some of them will be discussed in examples. So one of the most important implications is, what if the line charge is infinite? What if the line charge is infinite? It goes minus infinity and here it goes to plus infinity, and this is the distance d. This was the same distance here, d. So what happens when it becomes infinity? So I wanted to focus here. When it was not infinity, it made certain angle. Now as we go on increasing it, this angle will be increasing, and if you make this line reach infinity, this angle will reach, yes, you guessed it, this angle will reach theta tending to 90 degrees or pi by 2. The same thing is going to happen here. If this line goes to minus infinity below, then the angle this side would also reach beta tending to 90 degrees. And if both angles reach 90 degrees, what is going to happen to E perpendicular? So E perpendicular will be k lambda by d sine 90 plus sine 90, and that is 2, so you will have 2k lambda by d. What will happen to E parallel? Cos 90 both are 0, E parallel will be equals to 0. So for infinite wire, there will be no field along parallel. The only field that will exist will be E perpendicular. So we had an infinite wire, and if the wire was infinite, we learned that the field that will exist will be only E perpendicular, and that the value of E perpendicular will be equals to 2k lambda by r, or 2k lambda by d, where d is the distance. Now what if the wire is semi-infinite? Now there are various implications to semi-infinite, but let's consider the simplest case first. Semi-infinite. So semi-infinite, the simplest case in semi-infinite is that point P will be in line with the lowest point on the wire. That is the simplest case of semi-infinite. So we will have an angle alpha, and as you can see, the angle alpha is increasing and increasing and increasing, and alpha is tending to 90 degrees. But there is no angle beta, no beta here. So if there is no beta here, what is or what will be the field due to a semi-infinite wire? So let's talk about E perpendicular first. Do we remember the formula for E perpendicular? That was K lambda by D into sine alpha, that is 1 because sine 90 is 1, and sine beta because beta equals to 0, so that becomes equals to 1. And what will be equals to E parallel? If you remember the formula, K lambda by D cos beta, that is cos 0, and what is cos 0? Cos 0 is 1, and minus cos alpha, that is cos 90, that is 0. So again we'll multiply it with 1. So in this case, E parallel is also there, that is K lambda by D, and E perpendicular is also there. E parallel is there and E perpendicular is there, and both values are equal, and they are equals to K lambda by D. Now I'm still taking a semi-infinite wire, but I'm not going at the same level. Now I want you to see this. My point P, where I have to find out the field, is below the lowest point of the semi-infinite wire. So this is my semi-infinite wire, half infinite, semi-infinite. This is one side is going to infinity, that's for sure. But I don't want to find out the field here. I want to find out the field here. And if you look at the angles, I'll extend it here. The perpendicular distance is still D. If you look at the angles, this time this is the reference. Please take care. This is the reference. This is very important to note now. This is the reference. And reference, you remember what reference is? 0 degrees. And this is beta. And this is alpha. This is alpha. Now, what is the striking thing here that we notice? We notice that alpha and beta are on same side, isn't it? Alpha and beta are on same side. So if I have an E perpendicular and if I have an E parallel, there will be something different with the formula, because we are not taking beta minus beta to alpha. The limits are different this time because alpha and beta are on the same side. So we'll try to remember what E perpendicular was. E perpendicular was K lambda by D. Now I am going back to the basic derivation. If you might remember, that was sine theta, and the limits was from minus beta to alpha. But this time around, the limits will be from beta to alpha because they are on the same side of the reference. So the limits are going to be beta to alpha. So that will be equals to K lambda by D into sine alpha minus sine beta. Minus sine beta. If you might remember the formula for E parallel, that was K lambda by D into minus cos theta. Again, the limits were previously minus beta to alpha. This time they are going to be beta to alpha, not minus beta to alpha. And why not? I'm explaining it again. Beta and alpha are on the same sides of the reference line. So you'll have K lambda by D cos beta minus cos alpha. So what do we notice here? We notice that the formula for E parallel does not change. is same formula. But the formula for E perpendicular does change. The previous formula was sine alpha plus sine beta, and this time it is sine alpha minus sine beta. Now, I have a difficult but interesting question here. I had an infinite wire. You can see this wire starts from infinity, goes to infinity again. But I did something interesting with it. I took my wire, I bent it at a certain point. Just bent it at a certain point. Let me call that point as point O. So I bent the wire at point O. And now I want to find out the field at point P here, which is on the angle bisector. Angle bisector means this half angle is 30 degrees and this half angle is 30 degrees and the large angle is 60 degrees. So I want to find out the field at point P, which is the angle bisector, and at a certain distance distance d from point O. So I'll write this. The distance OP is equals to d, and the angle at O is equals to 60 degrees. So how do we find the field at point P? That is the question, and it's that simple as that. And then we want to find out the field at point P. So how do we approach this? We approach this by taking two half wires. Let me draw the wires here, and I'll use a lot of colors so that the solution may be clear to you. And angle bisector at point P, this is D. Now the first things first, what is the perpendicular distance not D, let's say some perpendicular distance. So this angle is 30 degrees. So what is the perpendicular distance of the first wire? Let me name this as first wire and let me name this as second wire. So what is the perpendicular distance of the first wire from point P? So if you see the triangle, that is D and 30 degrees, so this will be D by 2 because D sine 30 degrees, D by 2. Likewise, what will be the perpendicular distance between point P and the second wire? Same, D by 2. And now we have perpendicular distances. We are going to find out the fields. How do we find out the fields? Moving on to the next page. The wire again. And this time I'm going to draw it bigger. And this is the angle bisector. This is the angle bisector. This perpendicular distance is D. Now you must understand that at any point, there will be two fields. There will be an E perpendicular and there will be an E parallel. For the second wire too, there will be an E perpendicular and there will be an E parallel. To make things a bit clear here, what I have done is I have tried to color code this. The yellow color fields are due to the wire 1 and the green color fields are due to the wire 2. The color coding would make it a bit easier to understand. So let's start working on this. So this angle is how much? 30 degrees. This angle is how much? 90 degrees. You remember this distance was D by 2. This distance was D by 2 and this distance is also D by 2. Okay. 30 degrees, 90 degrees. So what is this angle going to be? It is going to be 60 degrees. If this is going to be 60 degrees, what is this angle going to be? It is going to be 60 degrees, right? Vertically opposite angles. Likewise, this angle here is 30 degrees. This is 90 degrees. This angle is going to be 60 degrees, obviously, and then this angle is also going to be 60 degrees. So we have two E perpendiculars. We have two E perpendiculars and both are at 60 degrees. Now, what is the angle between E perpendicular and E parallel? The angle between E perpendicular and E parallel, please take into account this point here. The angle between E perpendicular and E parallel is how much? 90 degrees. And this is 60 degrees here. So 60 degrees, 90 degrees. How much is this angle going to be? Can you see this angle? How much is this angle going to be? Show you in a separate diagram. I am drawing the red line from point O. This is point O. This is point P. This is E perpendicular. This is E parallel. We know that what do we know? We know that this angle is 60 degrees. We also know that this angle is 60 degrees. This angle is 90 degrees. So how much is this angle going to be? 30 degrees. Okay, so same diagram. Okay, so this is point O, this is point P, and let me draw the wire, the second wire, that is second wire. Now the perpendicular distance from the wire, this is E perpendicular and this is E parallel. You know that this angle is 30 degrees. Please take into account from here 30 degrees. This angle is obviously 90 degrees, so this angle is going to be 60 degrees, of course, and I'll have to extend the wire here. This angle is going to be 60 degrees again. So 60 degrees, 90 degrees, and what is this angle? This angle will be 30 degrees. That is what I was trying to show here. This angle is going to be 30 degrees. But now the diagram has got very confusing. Let me change the page. Particular distance. Drawing the wires again. Perpendicular bisector. So E perpendicular, E parallel. Likewise, E perpendicular, E parallel. And what is this angle? 60 degrees. What is this angle? 60 degrees. What is this angle? 30 degrees. What is this angle? 30 degrees. So let me mark them. This is E perpendicular, this is E parallel, this is E perpendicular, this is E parallel. All the green ones are due to the second wire and all the yellow ones are due to the first wire. Now the finding resultant becomes easy. It becomes really easy. You see, E perpendicular and E perpendicular, both the E perpendiculars are basically making an angle of 120 degrees. And both the E parallels, notice the E parallels, and both the E parallels are making an angle of 60 degrees. So we have to find out the vector sum of 4 forces, but we will take 2 at a time. So E perpendiculars first. So we'll have E perpendicular squared plus E perpendicular squared plus 2 E perpendicular squared cos 120 degrees. This will be the field E1. Can you show me the field E1? This is your field E1. What is E1? E1 is the resultant of E perpendiculars. So that will be equals to only E perpendicular, because cos 120 is minus half, so you'll get E perpendicular, and we'll solve for the value of E perpendicular. What about the other ones? The sum of E parallels, that will be E2. The sum of E parallels, that will be E2, equals to root under E parallel squared plus E parallel squared plus 2E parallel squared cos 60 degrees. How much is cos 60 degrees? Cos 60 degrees is half, so E2 becomes equals to root 3 times of E parallel. And this is your E2. How shall I show E2? This is your E2. This is your E2. Now what is the resultant field? Most simple terms. What is the resultant field? The resultant field is E1 minus E2. Draw the diagram again here in case you are getting confused. Right. So in this direction was E1, in this direction was E2, and the resultant field would be equals to E1 minus E2. Now what was E1? E1 was E perpendicular and E2 was root 3 times of E parallel. Now all that remains is to find out the value of E perpendicular and E parallel, and we don't have to do it for both the wires. We can do it just for one wire, because both wires are very similar. So what will be E perpendicular? So this distance is d by 2. This angle is 60 degrees, and the other angle, this side, alpha, is tending to 90 degrees. As you can see, the wire is infinite. So what will be E perpendicular equals to? E perpendicular will be equals to k lambda upon d by 2. By 2 mein 2 goes up, and we'll have sine 90, that is 1, minus sine 60, that is root 3 by 2. What will be E parallel equals to? E parallel like this. E parallel will be equals to k lambda by d by 2. Again 2 goes up. Cos 60, that is 1 by 2, minus cos 90 equals to 0. So that becomes equals to k lambda by d. And you can use the value of E parallel and E perpendicular to find the value of net field, that is E naught.